ladies and gentlemen. I would like to introduce Noel Markham, who is going to give the first real talk of Scala World 2016. And I asked around for how do I introduce Noel Markham, of course, and I found his colleagues who had a lot of things to say, yeah, he's a good guy, and he likes football.
Yeah.
Arsenal, I think.
No.
Of course, Arsenal, great team, good choice. And he's going to give, but more seriously, he's going to give an introduction to ScalaCheck, which is a testing framework that is the best testing framework.
Of course.
Of course. And I would like you all to give a very warm applause for his talk. Noel Markham, everybody.
Thanks. Hi, everyone. Yeah, has anyone had one of those dreams where they suddenly find themselves speaking in front of a lot of people at no notice? Well, that's kind of what's happened to me. So yeah, I've kind of stepped in at the last minute. This is a talk I've given before, so this was kind of ready to go. Have many people used ScalaCheck? Have we got people who use it? I can see a few. Yeah. And how about those who don't? Okay, all right. So probably less than half. Okay, so this is generally an introductory talk. So maybe for those who've used it, there'll probably be a lot of stuff that's already covered that you already know. Hopefully there's some new stuff. I've got some techniques as well, which hopefully will be useful to everyone. Like always, if something doesn't make sense or I'm going too fast, please do shout out and tell me. I believe I've got 45 minutes, so I think I've got more than enough to cover that time. But I'd rather people left knowing something than I get to the end of my slides and nobody really understood what I was talking about at all. Okay, so thank you for the kind introduction. Yes, I work for a company called 47 Degrees. We're one of the platinum sponsors here as well. So we're a functional Scala consulting group, and we tend to do consultancy roles focused on Scala, and also we do a lot of work with some open source as well. If this is something of interest, come and have a chat with me or some of my colleagues. We're around for the whole conference. So, okay, so what we're going to talk about today, I'm just going to give you a brief intro to ScalaCheck, maybe for those who've never seen it before. I'm then going to cover the important classes that really you need to get to grips with in order to use ScalaCheck properly. I'm going to show how we write some properties, and that's really going to be the bulk of my talk, is how we actually go about writing good tests. Because ScalaCheck it's a testing framework. It's kind of similar in a way to other things like maybe JUnit or Specs or Scala Test, but it's different it has different levels of working with it. And copying your JUnit tests into ScalaCheck is not always going to be the most productive. And you need to think about your code and your tests in a slightly different way in order to get the most value. So writing properties is probably what I want to spend most of my time on. And then towards the end, we'll talk about some tips and techniques and maybe some pitfalls around using ScalaCheck, and then a nice little bonus part at the end on boilerplate reduction. So I'll start with a brief example here. I'm going to include all the imports you need, and I'll make these slides available afterwards. So hopefully all the code you see should just run as long as you've got all the imports that have followed through the code. So for those who don't know what ScalaCheck is that you assert properties about your code. And so you say, given my code, I want to make sure that a certain rule always holds. And so say, for instance, we wanted to test that the length of a string wanted to test that the length of a string was correct. So we can start to think about properties that would always hold for, if we call length on a string, what is going to be correct. And so we ask ScalaCheck to give us a lot of strings, and we will say, whatever strings you give us, I want to make sure that the property in my code holds. And a really obvious, and maybe not even the best property we want to test would be, whatever the length of a string, it's always going to be greater than or equal to 0. I think that would always hold. And so what we've got here is this gives us a prop object, and then we can call check on this. And in this configuration, ScalaCheck will give our property 100 different strings, and it will run the code for each of those and make sure they all hold. Okay? And this works straight out of the box with SBT. So we can create some tests just in a class which extends a properties class. And then if we just call test inside an SBT session, that will then go and do our tests for us. Okay, so just a couple of things about what ScalaCheck is. Okay, so the way I like to think about it is a bridge between types and values. So for instance, the way I often describe this is that if we wanted to test some properties about Booleans, it can only ever return true or false. Like the Boolean type is set up that there are only two possible values, and like you'd never write a test to say if something is true, it is true. If something is false, it is false. Like that doesn't make much sense. But when we deal with maybe richer types, say even just an integer, but our APIs maybe only deal with a subset of the values that a type can have, then this is really where ScalaCheck comes into its own, where maybe we want to say whatever happens, the value that is returned is an integer, but it's always greater than 0. And then we can have that property hold, and that gives us so much more confidence about our APIs. Okay, and if you ever in your API, in your applications, you have, say, a whole class of stub data or sample data that you use in order to make sure your tests are all working, you should be using ScalaCheck instead. The randomized data that ScalaCheck gives you is a direct replacement for sample or stub data. And another way to think about it, and this is what we'll cover today, is that you actually open up a conversation with ScalaCheck, and it's about both your implementation and your tests. Is that ScalaCheck will turn around and say, well, for this input, your code doesn't work. And what does that mean? Does it mean that your test is wrong and you're maybe too comprehensive or not comprehensive enough in your test? Maybe your implementation is wrong. And it just opens this slightly different dialogue that you don't often see with something like a unit testing framework. And it's very thorough as well. You know, it will come up with cases you never even dreamt of. And that's one of the real benefits of using ScalaCheck. And what ScalaCheck isn't as well, it is not a random library. If you want randomness for whatever reason that's not testing, you do not use ScalaCheck. It does not give an even distribution over the type values, and it tends to focus on what would be corner cases. So if we start generating lots of integers, we will get a large range of integers, but they will tend to focus around 0, 1, -1, maximum integer, minimum integer. Those are often where the corner cases and where problems tend to occur in people's code. It will obviously check for random numbers that an integer can be, but it tends to focus on these kind of edge cases or corner cases. It's not a silver bullet. Using ScalaCheck does not make your code invincible. It's not fast. I'm not going to explain what I mean by fast. I'll let you think about that, about what exactly I mean. Okay, so here's some more examples just to get us warmed up. So say we wanted to test the absolute function on Scala's math class. Is that this seems like a pretty fair assumption to hold, is that if whatever integer we get, when we call the absolute value on it, it is going to be greater than or equal to 0. But no, it's not. Does anyone recognize this number? Does anyone know what this is? I think I heard that. Yeah, so it's the minimum value of integers, and probably most of you know that because the JVM uses 2's complement for binary notation, is that we have one more negative value than positive values. So negating the min value actually results in the same value. So what does this mean exactly? So we've got a problem. Is it a problem with our API? Is it a problem with our test? This is what I mean by the conversation. And then one thing we can do here is that we can assume, I think in this case, that this is not a problem with the API. You know, we want to be returning an integer. We just have this very strange case. Perhaps there's an option to a reason to have option here, and if we give the minimum value, we get a none. Otherwise, it's a sum with a positive number. But you know, whatever. But what we can do is that we can constrain the generation within ScalaCheck to say, only give me, when an integer is generated, it needs to hold this predicate here. And if it holds, then the test will pass, the test will run. If it doesn't hold, it's not a failed test. The test just runs, the property just runs again with a different value and checks that property, checks the predicate again, and will keep doing that until it's had 100 passes. Okay? Yet another example. So say for some reason we've written a reverse method that takes a list of any type and reverses it into another list of any type. And clearly this is that working? Clearly this is not production code, but let's say it's broken. For some reason, if the list is greater than a length of 4, it doesn't actually reverse it. So assuming that one of the properties of reversing a list is that the last element in a list is the head once it's reversed. Okay? That's a property that should always hold, and we want to say that it's like this for whenever a list is non-empty. Okay? And clearly that was going to fail. But what I wanted to show here is what ScalaCheck actually did, is that it's given us 2 results. It's given us this arg0 and then arg0 original. And this was the test input that failed. And then what ScalaCheck did is it did this technique called shrinking. And then it worked out what was the smallest set of data that would cause our test to fail. So as soon as it found a failing case, it iterated on that in order to work out what the smallest case was. And if you look here, actually, there's 6 elements in this list. And then it trimmed it down to 5. And then it also, just due to the nature of the way it works, it managed to shrink the values down. So actually the values probably didn't matter here, but notice that we needed to have some value in the list, because if it was 5 zeros, then our property actually held. So that's really comprehensive, I think. That's done quite a lot of work just to make sure that our property of reversing lists actually works. Okay, I've got another example here. So this one is dealing with list concatenation, and again, maybe this looks like a fair property to work with. Is that given 2 lists, is that the length of the first list should be smaller than the length of both lists combined. But of course it's not, because what we didn't think of here was that we can concatenate 2 empty lists, and then of course that fails. So again, this comes back to what I was saying here, is that this is a conversation, and probably what we've uncovered here is probably a bug in our test rather than any implementation. So we could have used the implication operator here again, or there's other things we could do as well. So what we could have said in this example is we want to only ever generate non-empty lists, rather than saying, give me a list, I will check if it's non-empty and then run my test. We'll just say straight up, we want non-empty lists. And we can do that with some APIs that ScalaCheck gives us in this gen object. And the for all method that I've shown a few times actually takes parameters as well. And so we can take these generators, and here we can say, I want a non-empty list of any old integer. I want 2 of these. And then these parameters follow through into our for all block. And then we can now make sure that makes sense. Okay, does that all make sense so far? Yep. Okay, great. So let's have a look at some of the important classes. And I've kind of started to touch on these already. So we've got this class called gen, which is short for generator. And what this does is this produces any value for a particular type, or a subset of those values. So what we saw earlier was there are generators to create any old list, but then we've also got a generator that only gives us non-empty lists. It's a monad as well, so hopefully most people understand what that means, and that means that we can use a few generators and combine those in some way to produce new generators as well. And ScalaCheck ships with many of these, so it really allows you to create quite rich generators that you often need for creating your own properties. And I've just shown a few here, and these are all inside the gen object. So we can create alphabetical strings, and this will create strings, but rather than anything inside the Unicode set, it will only give us A to Z, both uppercase and lowercase. There's a slightly more complicated one, posnum. As long as there's a type class of numeric for our type, it will give us a generator for that type. So as you'd imagine, most of the numbers you'd ever deal with inside the Scala API have a numeric type class attached to them. So we could create positive integers, positive floats, doubles, longs, whatever. And if we have our own type, maybe we want to use Spire's unsigned integer, as long as we have a numeric type class for that, we can use this method to create positive unsigned integers, which actually would be positive anyway. We can give a list or a sequence of something, and this will give us a generator that only ever gives us values from the given list. We can give a list of generators, and this will produce a list of things. We can produce a list of n things. For instance, if we wanted a list of 5, or maybe we have another generator that gives us a positive number, and then we could put that positive number into this so that we have complete control over the length of the list, while our test is able to create arbitrarily long lists. And there's also one in a different class, and we'll talk about this a bit later on, which is the arbitrary class. And this allows us to create arbitrary anythings. So as long as we have this arbitrary type class for a given type, this will use that to create values for us. Okay, and we'll just have a quick look at some of these. So if we look at, say, the posnum one, posnum returned a generator. There's a method on generator called sample, and that gives us these values here. If we call it multiple times, it gives us different values. As I said earlier, gen is a monad, so we can combine more generators in a more fun way, perhaps. So if we wanted a string that always started with an uppercase letter and then was followed by lowercase letters, if we're generating names for a form, for instance, this would work. And now we've got a brand new generator that we've just made up, and we could use this in our for all method, and it will always give us something that looks like this. You'll see a capital letter and then an arbitrarily long from 0 to n number of letters afterwards, which are always lowercase. Okay, so the other main class to work with inside ScalaCheck is the arbitrary type class. And all this does really is it allows the generators we've just seen to be summoned implicitly. So we can, if you remember the very early properties I was showing you, there were no generators being passed into our for all method, and they were just being summoned by the arbitrary. As long as an arbitrary existed for that type, then it was able to use those. But of course, we can create arbitraries for types that don't currently exist. Types for our own domain and our own APIs. For instance, like this. So if we had some kind of record case class, we could create our own generator for records, and then we can just wrap this inside an arbitrary object, and that means that we could then do things like this. Just a for all with no parameters, and then our block that follows for all will work with a record object, whatever that means. And then we can do whatever assertions we need to do inside our test. And then, as I pointed to earlier, there was this arbitrary method that existed on the arbitrary object. And as soon as we have an arbitrary implicit in scope, we could just call sample on this if this was of use. So hopefully you've started to realize by now that it's possible for a type to have more than one generator. We've looked at maybe 4 or 5 different ones for strings. We can all think of lots of different generators for numbers. We could have positive only, negative only, even only, divisible by 10, whatever. But then a question is, which of the generator instances we've seen should use for our arbitrary? And as a rule, it's generally the generator which produces the fullest range of values should be used in the arbitrary. Because if we go back here, if this record only produced if our arbitrary only produced records where the string parameter had 3 characters, but it's possible for a record to have as many characters as you want, then you might find that you're not getting the full value of the range of testing available because your arbitrary isn't producing the full range of values that are available as well. Okay, so that was a kind of a whirlwind intro to both ScalaCheck and the important classes. And really what I want to get across today is actually designing properties, and this is where a lot of people tend to find is a bit of a struggle with ScalaCheck, and we'll come across some of the pitfalls and how to get around those. So are people familiar with the game Yahtzee? Yes? No? Anyone not? Okay, it's very similar to poker, but played with dice. Okay, so I'm going to show a very, very kind of distilled down version of that, but these are basically, you have 5 dice and you roll them and you can re-roll some of them. And these are like the hands that you can create. So Yahtzee would be 5 of a kind. A straight is 1, 2, 3, 4, 5, or 2, 3, 4, 5, 6. A full house is 3 of one number and 2 of another. 4 of a kind, as you'd expect, and 3 of a kind, as you'd expect. Okay, and so say we wanted to write some API that looked like this. Given two different hands, which one is better? And the ordering I've got on the slide here, the higher up the list, generally the better that hand. So Yahtzee is better than 3 of a kind, and a straight is better than a full house, and things like that. So let's have a think about how we would try to test a method that looked like this. You could probably start to think of it already without using ScalaCheck. You'd come up with some different combinations and make sure one played off against the other and things like that. But what we're going to show here is we're going to let ScalaCheck do all the heavy lifting for us. So let's have a go at writing the test for this. Okay, so here's what we're going to do. We're going to generate 2 random hands. We're going to look at them and work out which one was better, and then we know that the better one should win. We will run it through our method and make sure that it wins. So an implementation might look something like this. So we've got our for all method, and we pass in 2 hands, so we can assume that we've implemented some arbitrary for hands. And then, we want to go through each of the dice, and if they're all equal, then we know we've got Yahtzee. We know that if they're all in a line, then we know we've got a straight, and so on and so on and so on. And then we can do that for both hands, and then we know which one's better, and then we can run it through our winner method and make sure that that worked. Okay, so what do people think of that? Well, it's not very good. But basically we've probably re-implemented our application code inside our test. And this is probably one of the problems people tend to have with that. And I had a conversation with someone yesterday, and they said, the problem I have with ScalaCheck is I end up re-implementing my production code inside my test. And that's exactly what's happened here. And while this works, it's not great. And so I'm sure we will. We're going to take a look at some better ways to work with this. So here's let's start again, and let's think about this again. Rather than generating hands, we're going to generate dice values. We're going to use these dice to construct hands, and then we know which one will win because we're constructing those, and then we make sure that the correct one wins. So that could look like this. So rather than hands, we're passing in dice. We've got 3 dice. And what we're going to do, we're going to compare that Yahtzee is better than a full house. So that's why we only need 3 dice here. And we want to make sure that FHA and FHB are different, because if they were the same, then it's not a full house because it's 5 of the same number, so that's Yahtzee. So we take our dice that have been generated, and we know that this holds now. And so we create a hand with 5 of the same, and then we create a full house with 3 of the same and another pair. We make sure that it works this way round, and then we make sure that it works that way round. And I think that's better. Then whatever dice combination we work with, we know that that's going to work and be a bit more comprehensive. But we still have a few things that we haven't covered here. So different permutations of full house dice positions. So just because we've got 3 in a row and a pair here, it could have AAB, AB, or BB, A, and all those different permutations. And that's not covered here. We want to make sure that our code was comprehensive enough to cover that. And also, we're only looking at one pair of hands here. And we want to compare Yahtzee with a full house and a straight and 3 of a kind and 4 of a kind, and then 4 of a kind with everything that's lower than that, and so on. And we actually come up with a quadratic number of comparisons we need to do, which, in fairness, for this problem is not very many and would definitely be okay to do this by hand. But I think we can have one more go, and I think we can do it better again. Is that rather than generating just any old hand or dice, we want to generate known hands. And then we want to make sure that the one that should win actually wins. So what we need to do for this is we need to create some generators. And we're going to create a generator for each winning hand. So the one for Yahtzee would look something like this. Is that we take this one-off method, which is on gen, and we pass in a list, and this is the list of all dice. This will give us one of those. We then create a hand from all 5 dice being the same one. And then you can see that there's 6 different permutations for this, and when we generate them, we're always going to get 5 dice of one value. And then this could be one for 3 of a kind. I haven't taken into account the different dice positions just for the slide, but the code I've got on GitHub for this does do that for some of the generators. And so what we do here is, look, we're using a full comprehension. We're taking advantage of the fact that the generators are monads, is that we want to pull out one of the dice, and then we want to pull out another dice, but not including the one we've already seen, and then the same again, not using the 2 we've already seen. So we end up with 3 different dice, and then we can put these into a hand, and we know that for 3 of a kind, we've got 3 of the same, and these 2 are different, and they're not going to be paired with each other as well. So we've got a couple of generators here, and then we could do that for all the different hands that are created. And then what we want to do is we want to order these generators to reflect which hand is better than which. And this is actually what we're testing. This is our test, in effect, is that we're saying that Yahtzee is better than a straight, better than a full house, better than 4 of a kind, better than 3 of a kind. And the really cool thing with the list here is that we're just using a plain old list to actually create the order for us. And then we've got one more step, that we can use ScalaCheck to partition this list, and it would look something like this. So we've got a for all, which given a number between 1 and the number of generators we've got, that gives us an index, and then we slice that list at that index. So then we've got 2 lists, and everything in the left-hand list or the first list will beat anything in the other list. And then what we can do is we can take these 2 lists of generators and pick one from each at random, and we know that whatever generator was picked will beat whatever generator was picked in the other list as well. And just to be completely clean and honest, this code here won't actually work because the API restrictions on ScalaCheck don't allow this. However, there are some really silly workarounds, but the concept is exactly the same. And again, the code is on GitHub and it's real and it all works as well. So then the final step is that we want to take one hand from each of these generators and face them off against each other, and straight away we know which one's won. And so our full code looks like this. So we looked at the first part here, and then look, we can nest these properties as well. So we can generate some numbers, work with those, and then use those numbers in another property as well. And so we take one of the generators from the winner, one of the generators from the loser, we then get some winning and losing hands. We then compare that they work both way rounds in the method, and that should just work. And again, this is not smoke and mirrors. All the code's up there for you to see. So the one thing that's quite uncomfortable with this, and it takes a while to get used to, is you don't really know what's being run, and you've just got to test or trust that you've written the code right and that it's all being tested right. And you might be inclined to put in a few cheeky print lines here to say, well, I'm testing this hand against this, and you have a look in the console and you're like, yep, that works, I'm all good. But again, ScalaCheck gives us some extra value here, and we have a bonus step of being able to verify what exactly was run. And there's a function called collect, and what we do, this is the method as before, but our property is wrapped inside this collect method. And this takes any type, not just strings, but I've used strings here. And I've said it's going to be this hand versus this hand, and then we run the property as before. And what we see when we run this inside SBT, we see something like this. So it did 100 tests, and 20% of those was a Yahtzee against 4 of a kind, and 9% of those was a straight against 3 of a kind. And this is what it did. And this gives real confidence that actually you've got a really, really nice comprehensive test here. And this has been built up from these really small, nice parts into this really good test that really feels to me like it tests our code quite thoroughly. Is everyone okay with that? Has that made sense? Yeah? Okay, cool. So just one thing to notice on here is that while I say this is comprehensive, notice that there's no full house against 4 of a kind. And when this test was run, that just didn't happen. So all the random permutations, that never happened. If this was plugged into a continuous integration framework, then every time you committed or ran the tests, it would do this, and this would come out. We can also do things which I'll show in a minute to run more tests. And I'm sure that if we'd run this 1,000 times or 1,000,000 times, the iteration of full house against 4 of a kind would have come up. And I know it did because I ran this more than once and I definitely saw it as well. Okay? So to finish off for the last 10 minutes or so, just talk about a few tips and techniques to get the real value out of using ScalaCheck. So I showed that implies operator before, which was a binary predicate in order to make sure that the generated code was valid for whatever you wanted to test. I would always suggest that if you can do something in a generator rather than relying on this implication predicate, to do that. So what do you think this returns? So we've got 3 integers, and then we want to make sure that all our integers are positive, and if they are, then the test passes. Any ideas? No? It actually fails. This will fail your build. And ScalaCheck gave up. It couldn't find enough permutations for this test, which, I mean, this blows my mind, to be honest, is that if you have this constrained, it gave up after 51 past tests because it was throwing away so many when it was generating negative numbers that it just thought, there's something wrong here, I'm bailing out. However, this test could work like this. So we've got this posnum, which is a generator we've seen, and this just works straight out of the box. So I would always say try to use implication where you've got maybe a single value you want to constrain, or it's such a simple thing that you're not going to run into trouble like this. I find with generators, they tend to make your code a bit clearer as well. Maybe there's a few more lines of code you need to use, but it tends to be a little bit clearer anyway. So talking of clarity, we can label our generators as well. So if we have a look at a test like this, so we take an arbitrary integer and an arbitrary map from integer to string, we want to check that we can get that value out of the map. And I mean, clearly this is nonsense. So we can't get anything out of an empty map, for instance. And while this case is quite simple, we could do something like this. So we can put labels on our generators, and then when it fails, we get some nicer labels. So rather than these, we get how we labeled it as well. So you can imagine if you had, a dozen generators into your property and 6 of them were integers and 3 of them were maps or whatever, you might find it hard to work out which one does which inside your test, especially if you come back to it when it starts failing 6 months after you wrote it. This just allows you a little bit of more flexibility in order to mark what the generators are for. Okay, and you can do some more labeling as well. As well as labeling generators, you can label properties, and this is better than just printing stuff out. So if we had a property like this, which just takes a pair of integers, and then this property really makes sure that if you've got two numbers, if you square the larger number, the value is higher than the square of the smaller number, which is a property that should always hold. This fails for some reason, and it might not be clear here as to why it failed. We know that if we have I as this large number and j as this large number, something goes wrong. But what we can do is we can put a label with the same operator we saw for labeling generators, and we have a string here which we can put anything on, is that when this fails, we then have the ability to kind of guide our user to what the problem actually was. And then in this case, this argument when it was squared makes this value, and this argument when it was squared makes 0, and then clearly we've got some problem with our API when things are going a bit crazy like this. And so this works much better than print lines, because with print lines, it's going to print for every iteration of your test. So even the successful tests, it will print. Even when a test fails and then it decides to shrink the values, when it shrinks those values, it runs the test again, which means it's going to print more and more stuff out. And that makes it really hard to work out when you got to your failing test, which was the lines that were actually printed, especially if you're printing more than one thing. But just being able to label the property that failed, and you can put anything you want in that label, including calculated data, that just works quite well. Okay, about 2 more minutes? Yep. Okay, I'm going to skip this. I'll put the slides up later. Integration with CI, as I said, there's a parameter inside SBT. So we could say, for instance here, which was what we were showing earlier, this runs by default with 100 tests. We could say this, which means let's make it run with 1,000,000 tests. And again, it still passes. It just takes a lot longer to run. Again, I'm going to skip over this just for time, but this is really quite interesting stuff. It's all explained in the slides. Okay, and one last thing I want to talk about, ScalaCheck Shapeless. What we've seen here is a lot of the boilerplate. There's a lot of boilerplate in order to get some generators working, especially with arbitraries, and a lot of the stuff we just often want the default case to happen. There's a library called ScalaCheck Shapeless, which uses Shapeless's automatic type class derivation. And what happens here is we can get that in our project with this SBT import. And then to show you a full example, I've kicked off a new console to show there's no smoke and mirrors. I create a new type that never existed before. I make one single import and another single import for arbitrary. And then what happens here is that I can call sample on this type, and it automatically generates them for me. And the only rule with this is it can derive any arbitrary as long as the type A is a case class or a sealed trait family of case classes, or an algebraic data type. And you can create the arbitrary values for all of the types inside the case classes. So if those are also those also follow these rules, or the generators already exist, that just works. The only thing to notice with this is that compile times can dramatically increase. So it's a bit of a trade-off in order to save a lot of boilerplate in your code. Okay, and then one final plug is a project that we've been working on at 47 Degrees called ScalaCheck DateTime. And this is a library to use sensible dates inside ScalaCheck. So you could imagine just arbitrarily creating dates. You might find you get some millisecond in the prehistoric times, and the next sample is some millisecond in the far future. And this allows you to really kind of home in on the values that make sense to you. So just a quick example here is that we've got this new generator that takes a parameter of a time and a duration, and then it will only ever generate times within that period. So between now and 7 days from now, all of these dates and times make sense, where now is actually the 1st of September in this case. This is a brand new library. We only launched it last week. There's more information on it here. That's about all I have time for. Again, I'll put these slides up. I'll put it on Twitter. And these are all real hyperlinks, so you can find the code for the talk and all the kind of nice tools that I use to help write this talk in the first place. And the ScalaCheck book is really, really helpful as well. So that's me. Thanks. Do we have time for questions or not?
No.
No.